Welcome. This video covers calculating the simple linear regression equation for case QQ, where we have two quantitative variables which are linearly related, as well as looks at the inferential components. In order to follow along, you will need the SPSS dataset pulse_step3.sav. We already have the data open in SPSS. To begin, we go to Analyze, Regression, Linear. We should verify that the relationship is reasonably linear using a scatter plot before conducting this analysis. We looked at height and weight earlier and found that, although it is best to analyze within each gender, the data are only slightly nonlinear when considered together. This will calculate the values needed for the simple linear regression equation for this data. For the regression, we must be careful to put the y variable, outcome or response, into the dependent variable list, and the x variable, predictor or explanatory, into the independent list. Generally, we will conduct only one regression at a time in this course. Drag weight into the dependent list and height into the independent area. In statistics, add to the estimates and model fit the confidence intervals. You might also select descriptives if you wish, and click Continue. In plots, we want to create a few plots of the residuals. The first two are easy. We simply select the two checkboxes for histogram and normal probability plot. This is different from a QQ plot, but provides a similar way of checking for normality. And getting the QQ plot would require us to export the residuals and then explore them in the way we learned for one quantitative variable. This is possible, but not necessary. The other plot we must create. We pull the z-resid into the y area and z-pred into the x area. You can create additional plots by clicking Next. Click Continue when you have these three plots requested. The Save option does allow you to save the residuals into your dataset and explore them further, but we will not do that here. We don't need anything in Options, Style, or Bootstrap. Click OK to see the results. Since we asked for the descriptives, we get the summary statistics for our two variables. We also get the correlation. Notice that here we obtain the one-tailed p-value. Be careful, as for results in this course, we want the two-sided p-value given by using correlate instead. Then there is some information about the variables entered, removed. This is more for multiple regression, which is beyond the scope of our course. Then we have the model summary. Of interest here is the R-squared value of 0.550. This can be interpreted by saying that this model using height explains 55% of the variation in weight. Then we get the overall ANOVA table. Regression and analysis of variance are mathematically the same process, but the one-way ANOVA is a special case, as is simple linear regression. This table provides an overall p-value of whether the model explains a significant amount of variation. In this case, the overall p-value is 0.000, and thus this model does explain a significant amount of the variation in weight. Then we get a table of the coefficients, which we've seen before. Here we've added the confidence intervals for the parameter estimates. If the intercept is meaningful, then this may be of interest, but in this case the intercept represents the mean weight for someone with a height of 0, which is not possible in practice. The confidence interval for the slope is of interest, as this provides bounds for the increase or decrease in the mean response for each 1 unit increase in the explanatory variable. The row labeled constant is the intercept and is negative 121.173. The row labeled with the x variable label, in this case height in centimeters, is the slope. Here it's 1.085. So the regression equation would be y hat equals negative 121.173 plus 1.085 times height. The slope implies that on average for each 1 centimeter increase in height, the mean weight increases by 1.085 kilograms. And the 95% confidence interval suggests this increase could be as low as 0.895 to as high as 1.275. Finally, there is a summary of the residual statistics. For the graphs, we get a histogram of the residuals with a normal curve overlay. We want the residuals to be normally distributed, which by this graph they seem to be. Then we get a normal PP plot of the residuals, which is similar to but scaled differently than the QQ plot. It will always match at the endpoints. We're still looking for the points to follow the line in order to be able to say the plot is reasonably normally distributed, which they do here. Finally, we get the scatter plot of the residuals on the y-axis versus the predicted values on the x-axis. We're looking for random scatter of relatively equal spread around the center, regardless of the location on the x-axis. If we see any pattern, it can indicate nonlinearity or non-constant variance, depending on the type of pattern. Both of these issues are violations of the assumption of this method. The more harsh the violation, the more concern we would have. In this case, there is some evidence of non-constant variance, in that for large values on the x-axis, there seems to be more variation. Possibly we have two clusters illustrating the different genders. We could investigate further by analyzing the two genders separately. We will save this output as topic 9e.spv. That's all for now. Thanks for watching.